Hello and welcome to this video where today we're looking at time dilation as part of the AQA Unit 5 Turning Points module. So these are the three things that we need to know. In a previous video we looked at the Michelson-Morley experiment and we saw that the speed of light doesn't depend upon either an observer or the source of the light. And so that led Einstein to look at things to develop the special theory of relativity, which is where time dilation comes from. So from a time dilation point of view, these are the things that we need to know. Before we can actually look at and calculate things about time dilation, we need to know what these things are. So we need to define what an inertial frame of reference is. We then need to look at how you calculate time dilation and look at the experimental evidence for time dilation. So before we start, we'll look at inertial frames of reference. Basically, an inertial frame is just a set of coordinates for a particular person. So I'm sat on a chair at the moment, so this is me. I have some certain coordinates in space. So I've got an x coordinate, a y coordinate, and a z coordinate. If, however, somebody is sat on a bus and they drive past my house at the minute, they'll be in a different inertial frame, provided they're moving at a constant speed. So they're sat here. So they've got their own x, y, and z coordinates. But for me, from my point of view, their coordinates are changing. But for them, their coordinates aren't. So their reference frame, the measurements that they would take for them, make up their own inertial reference frame. My inertial reference frame is mine and theirs is theirs. And the difference between these two inertial frames is that this one is moving at a constant speed relative to this one. You could also argue that this one is moving at a constant speed relative to that one. And that's where the idea of relativity comes from. You can look at things from each other's point of view. So as far as I'm concerned, I'm sat still and this person's moving on the bus. As far as they're concerned, they're sat still on the bus and I'm moving past them. It's actually impossible to say who's actually really moving unless you experience a force, and we'll come on to that in a second. But if one person is moving at constant speed relative to another, then we can say that both of these people are in an inertial frame. So this person's in an inertial frame and this person is just in a different inertial frame, and this one is travelling at a constant velocity compared to this one. A non-inertial frame is one where the frame is accelerating. So, for example, if the person that's sat on the bus is sat on some traffic lights and then the bus starts to move away, that's a non-inertial frame. And the special theory of relativity doesn't account for things that accelerate. So it only works for things that are moving at a constant speed. So a non-inertial frame is one that's accelerating. So examples of that are obviously things that accelerate in a straight line, also things that move in a circle. So if you're moving in a circle, you're accelerating towards the centre of your circle constantly, and so you're in an accelerating frame of reference, and so therefore you're not in an inertial frame anymore. A correct definition for an inertial frame from the AQA point of view is one in which Newton's first law is true. If you remember Newton's first law, basically that an object remains at rest or at constant velocity unless an external force acts on it. Well, if I have a ball that's sat on a table in my frame of reference here, and it's just sat there, then it will basically continue to sit there stationary relative to me unless somebody pushes it. From the person's point of view on the bus, that what they'd see is they would see the ball moving at a constant velocity. So there's no external forces acting on it, so therefore it's travelling at a constant velocity, so Newton's first law is true for both of us. If, however, you're in an accelerating frame and you look at this ball, what you would see that the ball is so let's say that this thing is accelerating and it's moving away in this direction, they'd actually see the ball accelerate in this direction here, but there's no forces acting on it. And so in this case, Newton's first law isn't true, because what you would see is no forces acting on this ball, but it would accelerate, simply because you're accelerating. So that's why we can say that this thing is a non-inertial frame of reference. So Einstein's theory of relativity that we're going to look at holds provided we're going to think about two points of view. We're going to think about, for example, an observer's point of view and something that's moving, but they're always going to be moving at a constant speed relative to each other. They're not going to accelerate. And so when you put the Michelson-Morley experiment together with the idea of inertial frames, then Einstein based his theory of relativity, which is what we're going to look at next, on two postulates, or basically two ideas that make up his theory. If either of these two things are wrong, then it means that all of his theory is wrong. So postulates basically is just like your starting point for a theory. You need to know these off by heart because in an exam you can be asked these. Basically, you can be asked what the two postulates of special relativity are. In other words, what the two main ideas of special relativity are that the whole theory depends upon. So the first one is that the laws of physics are the same in all inertial frames. So it doesn't matter if you're moving relative to somebody else. So, for example, the conservation of energy is the same whether you're sat still in your room or whether you are moving on a bus compared to a constant velocity compared to somebody else. The laws of physics are exactly the same. And then the second one, which is based on the Michelson-Morley experiment, is that the speed of light is invariant in free space. What that means is that the speed of light is the same when basically free space is a vacuum or empty space. So no matter who you are, if you see light travelling in free space or in a vacuum, you always measure the same speed of 3 times 10 to the 8 meters per second. So Einstein came up with his theory of relativity, and he basically said that the speed of light is invariant for everybody. It doesn't matter if I'm sat here and someone else is here and they're moving at half of the speed of light, so they're moving at 0.5 times the speed of light. If I shine a beam of light like this from a torch, for example, I'd measure this to be 3 times 10 to the 8 meters per second. So I'd measure the speed of light to that, but so would they. So the speed of light, it doesn't make a difference what you're doing. The speed of light is the speed of light no matter what. So he basically said, okay, so if the speed of light is a constant and speed is basically a combination of distance and time, basically, so speed is distance over time, then either something strange is going on with the distances or something strange is going on with time. So we're going to look at the point of view of what happens with time. In the next video, we'll have a look to see what happens with distances. But for the moment, we're looking at time because we're looking at time dilation. So what this basically says is that if you're moving, you experience time differently to somebody who considers themselves to be at rest. So if we go back to our person that's on the bus, the person's watch on the bus actually ticks at a very different rate to the person's watch that's basically sat still. What it basically means is that you can't really agree on what time it is. Now, if you're travelling very slowly, these effects are incredibly small. So from an everyday point of view, it doesn't really matter. It only really matters when you get close to the speed of light. And Einstein came up with this equation here. So he basically said, right, okay, let's imagine that we define somebody to be stationary, or an event happens and we know how long that event is in the inertial frame of that particular event. So let's imagine, for example, that somebody switches a torch on and off. So they make a flash of light with their torch, and the torch you're sat still compared to the torch. So the torch is in your rest frame, and you switch it on for 2 seconds. The time in the rest frame of that event, which is in other words, the time in the rest frame of the torch, is this t0 thing here, and this is called the proper time. And the tricky bit with this is making sure that you're always dealing with the proper time rather than the one constant compared to what you're moving. So if you think about your inertial frames of reference, your torch is just sat there. And so the time in this particular frame is your proper time. This t here, if we go back to our other frame, if we imagine the person on the bus, what they're going to measure their time, and it's potentially going to be different to the proper time if this bus is moving incredibly quickly. So this equation links the time of the moving object, if you like, or the moving observer, to that of an observer that's stationary compared to that event. So this is the proper time, and this is sometimes called the relativistic time. The V is basically the speed of your inertial frame, And if you think about it, we're always going to have an inertial frame that's sat still relative to, for example, our torch. So it's also going to be the speed of the torch if we're in this frame and we watch the torch move. So that's the speed of our inertial frame. Let's try and spell that properly. Inertial. So that's the speed of our inertial frame, and c is the speed of light. So basically, if we know how fast the thing is moving, and we know the speed of light, and we know the proper time, we can work out how long it would take for us to see that torch flash, for example. We'll have a look at that in a second. So, like I said, this proper time, it's getting the right time in the right place. The speed is fairly straightforward, and the speed of light is the speed of light. It's that 3 times 10⁸ meters per second, so it's getting the right time. So here's an example. We have a spacecraft. It's travelling past the Earth at a speed of 0.9 c. In other words, 90% the speed of light. It flashes a light for 3 times 10 to the minus 3 seconds. So there's a really quick flash of light. We want to know how long this signal would we see this signal on the Earth. So what we've got, if you think about it, the Earth's here, your observer person is here, and the spacecraft is flying away or past the Earth or whatever, and it's travelling at 0.9 times the speed of light. And on the spaceship there is a torch, and they flash this torch for 3 times 10 to the minus 3 seconds. So we're going to use this equation. So what we need to do is we need to say, right, am I working out this time or am I working out this time? Well, the light is flashed for this long on the spaceship, or on the spacecraft. So for somebody sat on the spacecraft, this is how long it takes for the light, basically how long the flash of light is. So according to us, this is the proper time. So in actual fact, what we can consider is we're on the spaceship and we flash the light, and actually we're not moving. What's happening is the Earth is moving this way. So this is the moving observer. So the time of this person is our relativistic time. The time on the ship is the proper time. So now we've decided that, we can then just put our numbers into our equation. So we've got t is equal to t naught, so 3 times 10 to the minus 3 seconds, over, I'll write it slightly differently, 1 minus, well, the velocity of the Earth relative to the spaceship is exactly the same as the velocity of the spaceship relative to the Earth, so 0.9 c all squared, divided by the speed of light squared, and that's square rooted, so to the power of a half. So if we just simplify this, because there's a nice little trick we can do in a second, that's 10 to the minus 3 over 1 minus 0.9 squared is 0.81, and c squared over c squared, all to the power of a half. Well, the c squared on the top and the c squared on the bottom cancel each other out, so I've just got 1 minus 0.81. So if I simplify that a little bit more, I get 3 times 10 to the power of minus 3 over 1 minus 0.81 to the power of a half, or square rooted. And if I do that on my calculator, I get 7 times 10 to the minus 3 seconds, like that. So the people on the spaceship flash it for 3 times 10 to the minus 3 seconds. Because the Earth is moving really quickly compared to that of the spaceship, the people on the Earth actually see it last more than twice as long, simply because this thing is going really quick. Deciding this thing is the really tricky bit. The only way you can do that really is by just doing lots of practice. So getting lots of past papers and doing lots and lots of practice to see, to make sure that you can definitely do that. In terms of evidence for actually that this actually works, this is one thing that the exam board like, and they ask you this kind of question from a couple of different points of view, and I'll show you the second point of view in a sec. But basically what we've got is we've got some muons that are created, and when cosmic rays come in, they hit into the nuclei of oxygen, nitrogen, and things, and they create muons. So you've got muons created in the atmosphere. You can measure the speed of the muons, and if you've got, for example, a mountain, you could put a lab at the top at A, and you could put a lab at the bottom at B, and you know the distance between these two labs. You can measure the intensity of the muons at A, you can measure the intensity or how many muons you've got at B, and you can compare them. So we're going to do this without relativity and with it. And basically what we're going to try and do is we're going to work out the intensity of the muons at the bottom compared to the top. So we're going to start off basically by, first of all, working out the time it takes for the muons to go from here to here. And we're going to do it without any relativity at all. So the time it takes to go from there to there, time is just the distance divided by the speed. Well, the distance is just 2,000 meters because our mountain's 2,000 meters high, and the velocity 0.996 c. And if we put in c as 3 times 10 to the 8, what we find is the time it takes the muons to get from the top to the bottom is 6.69 times 10 to the minus 6 seconds. So that's the first bit. Now, we know that the half-life of the muons is this, so it's 2.2 microseconds. So we can work out how many half-lives go by from here to here. So the number of half-lives, number of half-lives as t a half, is simply equal to the time it takes to go from the top to the bottom, 6.69 times 10 to the minus 6, divided by 1 half-life, 2.2 times 10 to the minus 6. And so if we do that, we get 3.04. So it takes 3.04 half-lives to go from here to here. And if we remember back to our nuclear physics, the intensity or the proportion at the bottom compared to the top is just equal to 1 over 2 to the power of n, where n is the number of half-lives. So 1 over 2 to the power of 3.04. And if we do that, we get roughly 0.12. In other words, 12% of the muon should get from the top to the bottom. Unfortunately, when you actually do this experiment, you get a number of about 80%. So this is quite clearly wrong. It's a huge difference compared to what the actual experimental numbers are. So that's what happens without relativity. We'll have a look and see what happens with relativity. So we know how long it takes. We're stood here, so we're these observers that are watching these muons go by. Now the muons are decaying with a half-life of this. So if we were travelling along with the muons in their rest frame or their inertial frame of reference, we would measure this. So from a muon's point of view, they're sat still, they're decaying with this thing here. So for them, if you like, the proper time or the proper half-life time, so the rest half-life of the muons is equal to your 2.2 microseconds. Because we're moving relative to them, then we will measure a different time. So let's work out what that time is. So the relativistic time is equal to the proper time. So that's your 2.2 times 10 to the minus 6 seconds over 1 minus, and then we've got 0.996 c all squared over c squared, and that whole thing on the bottom is to the power of a half. And if we do that on our calculator, we end up with a time of 2.46 times 10 to the minus 5 seconds. So what that really means is that despite the fact that these things are decaying, at least according to them, if they're sat still at 2.2 microseconds, the half-life, because they're moving relative to us, has changed. So we would measure their moving half-life to be 2.46 times 10 to the minus 5 seconds. It's got longer. So we can do the same thing that we did over here. So the number of half-lives now, well, it still takes the same amount of time to go from the top to the bottom, which is our 6.69 times 10 to the minus 6. But the half-life that we now measure, because we're moving relative to these muons, is this thing, 2.46 times 10 to the minus 5. And if we do that, we get 0.272. And then we can do the same over here. The intensity at the bottom, or as a fraction of what we started off with, is again 2 to the power n, where n is the number of half-lives. So it's 1 over 2 to the power of 0.272, and perhaps unsurprisingly gives us 0.83. So in other words, from a calculation point of view, approximately 83% of these muons should get from the top to the bottom, which compares incredibly favourably with actually what is observed. So without relativity, doesn't work. With relativity, does. So that's your experimental kind of evidence, if you like, for relativity. Now, when it comes to exam questions, they can ask you this sort of thing. They often ask you about half-lives. Sometimes what they do is they give you a simpler situation. They'll basically say there's a detector here and a detector here, and a beam of particles fly by, and you know the half-life. You can measure the intensity there, and you measure the intensity there, and they'll ask you to work out, for example, how many particles are left, or they in like they have here. Alternatively, they could ask you to work backwards, and they could ask you to work out, for example, how fast the particles are going. So you basically have to start off with these numbers and work backwards to this thing over here. So in terms of what we needed to know, we need to know what inertial frames were. Well, they were simply a set of coordinates that are moving at a constant velocity relative to each other. How to calculate time dilation, which was this equation here, and then finally experimental evidence for time dilation, which is our muons over here. So that was time dilation for the AQA turning points module. Thank you very much for watching. I'll see you again soon.